Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to another lecture of Physics 2. This is lecture number 3, and today we will study topics from chapter number 16. The title name of the chapter is Waves. The main topics of today's lecture are transportation of energy. We will study 3 different methods with which we can transport energy, and then we will also present the types of wave, which are 3: the mechanical waves, the electromagnetic waves, and the matter waves. But in this chapter we will focus on the mechanical wave, and the further types of mechanical waves are the transverse wave and the longitudinal waves. We will define them separately. We will study the necessary parameters for waves, and our final topic will be to derive an expression for the speed of waves, and will present an example which will explain the parameters of a wave. So let's start our first topic. Our first topic is about transportation of energy. We use 3 different methods to transport energy from one point of the space to other. The first type is the macroscopic transportation. In this transportation, the energy is transported due to motion of visual particles, and these particles may be small or very large object. For example, if you are seeing that the object is transported from one point to another point, so energy is associated with these objects, and this transportation of energy is known as macroscopic transportation of energy, in which you can see the object with your naked eyes. The second transportation is the microscopic transportation of energy, in which energy is transported by very small particles like electron in a conductor, and you cannot see the electron in a conductor, and these energies are related with the kinetic energy because we transport energy. So the main type of this energy will be the kinetic energy, and the macroscopic kinetic energy is a high quality energy, while the microscopic kinetic energy is more disordered and low qualities, because these particles, the electrons, are in random motion, so there is more disorderness. Another way to transport energy is due to waves. So waves are massless carrier. In this lecture we will only focus on waves. First we will study the types of waves. There are 3 types of waves. Mechanical waves. Mechanical waves are those waves which need a medium for its propagation, and they are governed by Newton laws, and they can exist only within a material medium. For example, wave in a string, wave on a water surface, and sound in air. Wave in a string, the string is a material for this wave. Wave on a water surface, so water is the material medium, and air is the material medium for the propagation of sound. Without these mediums, these waves cannot propagate from one point to another point. The second type of waves are the electromagnetic waves, and these waves require no material medium for its propagation. So these waves, the electromagnetic waves, can move without a medium, and it can also move within the material medium. The examples of electromagnetic waves are visible in ultraviolet light, radio and TV waves, microwaves, X-rays, and many more. and all the electromagnetic waves travel through a vacuum at the same speed, which is 3 into 10 raised to power 8 meter per second. The symbol for the speed of light is c, and it is a universal vacuum constant. The third type of waves are the matter waves, and these waves are associated with the electron, proton, and other fundamental particles, and these waves were presented by de Broglie, and the wavelength of these matter waves are known as de Broglie wavelength. Mechanical waves, we restrict ourselves to mechanical waves, those waves which need a medium. There are two types of mechanical waves, the transverse waves and the longitudinal waves. In this slide we will discuss the transverse wave. One way to study the waves is to monitor the waveform, that is the shapes of waves as they move. We consider a wave in a string that moves from left to right, and we fix one end of the string and the disturbance is sent from the other end, and you will see that the crest and trough are formed. The upper part of this waveform is known as the crest, and the lower part of this waveform is called a trough. From figure it is clear that the disturbance moves to right while particle of the material medium, that is particle of the string, moves up and down. So this pattern is known as the transverse wave, and we can define it as if the motion of every oscillating string element is perpendicular to the direction of the wave traveling, then the motion is said to be transverse and the wave is said to be transverse wave. So simply, if the motion of the particle of the string, if the motion of the particle of the medium is perpendicular to the direction of the propagation of wave, then such a wave is called the transverse wave. Example of transverse waves are the ripple on the water surface and the wave in a string. These are the examples of the transverse wave. The second type of mechanical wave is the longitudinal waves. In figure, an air-filled pipe is shown. If you suddenly moves the piston rightward and then leftward, you send a pulse of sound along the pipe. The rightward motion of the piston moves the element of the air next to it rightward, changing the air pressure there. Increase the air pressure while moving the piston leftward reduces the air pressure next to it. Compression and expansion elements are developed in the air pipe. This is compression part of the medium and this is the expansion part of the medium, while particle of the medium oscillate along these compression and expansion. So the longitudinal waves are also now known as the compressional wave. We can define the longitudinal wave is if the motion of an oscillating element is parallel to the direction of the travel of the wave, then the motion is said to be longitudinal and the wave is said to be longitudinal waves. And as earlier in the transverse wave, crest and trough are formed. Here the compression and expansion are formed. So the pattern in which the compression and expansion are formed is known as the longitudinal wave form. An example of the longitudinal waves are sound and spring waves are the common examples. Parameters of a transverse waves. We are only focused on the transverse waves in this chapter. As in transverse wave, the particle of the medium vibrate perpendicular to the direction of the propagation. So we need two axes to describe the transverse wave. The x-axis, which is taken for the propagation of waves, and the y-axis, in which the particle oscillate, that is, particle moves up and down. So we consider that axis as a y-axis. Or consider a sinusoidal wave that is traveling in positive direction of x-axis. The element oscillate, that is, particle of the medium oscillate parallel to the y-axis. At time t, the instantaneous displacement of the element located at x position is given by y, which is function of position and time. This is the instantaneous displacement of the particle, which is equal to ym sine kx minus omega t, where ym is known as the amplitude, the maximum displacement of a particle which is in vertical direction, and the instantaneous displacement varies from 0 to ym. So the displacement of a particle can be varies from 0 to ym. So we need an oscillating term. So there may be cos as well. Sine and cos are the sinusoidal function. So this term as a whole is known as oscillating term, in which there are a phase in the brackets. The phase is a unitless term which may contain many other physical quantities like k. K is known as the angular wave number. Later we will derive the relation between wavelength and angular wave number. The omega is the angular frequency or angular velocity. In previous lecture we define it in detail, and the negative sign show that the x-axis show that the propagation of the wave is the along the x-axis, and the negative sign show that the wave move in the positive x-axis. In this slide we will develop a relation between wave number and wavelength, which are the parameters of a wave. And first we define the wavelength. The wavelength of a wave is a distance between consecutive same phase point of a wave, or the distance between two consecutive crust or trough in case of transverse wave, or the distance between two consecutive compression or expansion in term of a longitudinal wave. We develop a relation, mathematical expression for the transverse wave, in which particle of the medium vibrate in a y-axis while the disturbance moves along the x-axis, and we write the expression y, which is function of position and time, is equal to ym sine kx minus omega t. So we are going to develop the relation between wavelength and angular wave number. So we took two position of the particle, one at x is equal to 0 and the other one is at x plus lambda distance. So in both equation we put x is equal to 0. So first we will put x is equal to 0 in this equation while the position will remain the same. So we will get y is a function of position only is equal to ym sine kx. The time term vanish, and we call it equation number 1. Now at the same time we are just change the position of the wave. So at x is equal to x plus lambda, our particle position will be ym sine k. For x we write x plus lambda. This is the new position and we call it equation 2. We multiply the wave number with x and with the lambda. So we will get sine kx plus k lambda, and we call it equation 2. So these particles are at the same phase points, and equation 1 and in equation 2 the vertical displacement of the particle is the same because they are the same phase point. So the right hand side of equation 1 and 2 equals, in if you look at this equation, sine kx is equal to sine kx plus k lambda. So here is the extra term k lambda, and this equation is only possible if the k lambda term equals to 2 pi radian, and from this equation we can write k is equal to 2 pi by lambda. And here we can define the angular wave number is the number of cycles. This is number. For one cycle we have 2 pi radian and it can be more, so we can define angular wave number is the number of cycle per unit length. Lambda is length element and the SI unit of k is radian per meter. The phase constant and speed. In this slide we will derive the formula for speed of wave, but first the phase constant. Sometime at x is equal to 0 and t is equal to 0, it is not necessary that the vertical displacement of the element is equal to 0. In this case the wave function can be written as y, which is function of position in time, is equal to ym sine kx minus omega t plus phi. So if we put x is equal to 0 and t is equal to 0, and then the vertical displacement of the particle may not be equal to 0, and we insert the extra term phi, which is known as the phase constant. So it will represent a number in term of degrees or in term of radian, and this equation is for the traveling waves and it can carry energy from point to point. And as the wave travel, the shape of the wave will not change, and we say that the phase is constant, the whole argument is constant. And if we differentiate this phase constant with respect to time, so we will get k dx by dt. We will differentiating each term of this argument. So k is constant and we will only differentiate position with respect to time, minus omega, the differentiation of time with respect to time is equal to 1, so we will left only with omega, and phase constant, this is constant, so the derivative of constant is always 0, and we have also the constant on the right hand side, so the right hand side will give us also a 0, and this implies that dx by dt is equal to omega divided by k. We shift minus omega on the right hand side of the equation and then divided by this term, so the rate of change of displacement is equal to omega by k, and the time rate of change of displacement is known as velocity. So velocity of a wave is equal to omega divided by k. And from previous lecture we developed a relation between angular frequency and natural frequency, and in this lecture we developed the relation between wave number and wavelength. So put the value of omega, which is equal to 2 pi f, and the value of k, which is equal to 2 pi divided by lambda. 2 pi will cancel with 2 pi and we will left only with f lambda. Velocity of a wave is also equal to f into lambda, where f is the frequency of a wave and lambda is the wavelength of that wave. In order to understand the different parameters of a traveling wave, here we present an example. In this example, an expression of particles of a medium is given as y, which is function of position and time. This is the instantaneous displacement of the particle of the medium, which is equal to 0.00327 sine 72.1 x minus 2.72 into t. So you have to compare this expression with the expression given for the transverse wave, which is equal to y is equal to ym sine kx minus omega t. When you compare this expression with the said expression, you will observe that your amplitude will be equal to 0.0327, because at the left hand side of the sinusoidal function we have amplitude. So this will be our amplitude. And in the oscillating term, both terms are known as phase. So in arguments we have kx. So k is 72.1 radian per meter. We took them in a standard units. And then minus omega t. So this is the angular frequency, which is equal to 2.72 radian per second. Find the wavelength of the wave. So we will use formula lambda is equal to 2 pi by k. From here you can insert the value of k and find your wavelength in meter. And then we can find the period of this wave, what time it would take to complete a single cycle. So the time period formula is t is equal to 2 pi divided by omega, and you can take omega from here and insert there. So you will get the time period of the given expression. And similarly, the frequency can be found as f is equal to 1 divided by t. Put the value of t over here and get your result in hertz. Or you can also write the formula for f, which is equal to omega divided by 2 pi, and omega is given, you can divide it by 2 pi to get frequency. Velocity of the wave is given by omega divided by k, and put the value of omega and value of k from the expression, you will find the speed of this wave. And finally, find the displacement when position and time is given. X is equal to 22.5 centimeter and the time is 18.9 second. So when we insert the value of x over here and the value of t and calculate this phase and then apply sine and then multiply it with the amplitude, so we will get 1.9 millimeter. Remember, I took 22.5 centimeter as 0.225 because I convert them into the standard unit, which is meter. So the instantaneous displacement of the particle from the origin is 1.92 millimeter. Let's summarize our today's lecture. What we have learned today, we have studied different types of energy transportation, which are macroscopic, microscopic, and through waves. And then we focused only on waves and discussed the types of waves, and types of waves were electromagnetic waves, mechanical waves, and matter waves, and we restrict ourselves to mechanical waves and discuss its types, which are the transverse waves and longitudinal waves. In transverse wave, the particle of the medium vibrate perpendicular to the direction of the propagation, while in the longitudinal waves, the particle of the medium vibrate along the direction of the propagation. And then we have studied some parameter like the amplitude, instantaneous displacement, angular wave number, frequency, and speed of a transverse waves. In next lecture, we will study a tool in which we can add two waves known as the superposition principle, and then we'll study the effect of the superposition principle, which is the interference phenomena and the standing waves. In the interference phenomena, we just combine two waves and study the resultant, and in standing wave the energy is trapped between 2 points which are called nodes, and we will study them in detail. I hope you will understand this lecture, and if you have any question or difficulties, you can contact me on my email. Thanks and Allah Hafiz.